Hello and welcome to our lecture. Today we're talking about two things. We're talking about the L'Hopital's rule, which you may be familiar with, but this time we're going to prove it. And we're also going to talk about the function that is continuous at every point of its domain, yet it is nowhere differentiable. The reason why this function is important is because it shows quite clearly that there is no converse to the theorem that we had that says that differentiable functions have to be continuous. So continuous functions don't have to be differentiable. They don't even have to be differentiable on tiny intervals. Continuous function can be very, very wild, maybe completely non-differentiable. Another reason why this function is somewhat important is because it's going to foreshadow some of the techniques that we're going to discuss in chapter 6, namely the series of functions and whether or not the property of continuity can transcend the limits and say the infinite summation of continuous functions. Will it be continuous? Will it be differentiable? And so on. So let's go right ahead. And remember, the L'Hopital's rule was talking about the ratios of the functions and their limits. So let me state precisely what the L'Hopital's rule is. You may remember there were two cases. One of the cases, and when the ratio of f of x and g of x has two functions, both f and g converge into 0, and the second case when both f and g converge to infinity. Strictly speaking, in the second case, only g has to converge to infinity, but when f is not converging to infinity, it's not really an indeterminate rule. And so we don't really need to use the L'Hopital's rule in that case. That's why you mostly concentrated on the case infinity over infinity. And we're going to do it the same way. We're going to consider two possible cases. The case when both f and g go to 0, and the case when g of x goes to infinity. Both cases of the rule are actually theorems. And this theorem requires f and g be continuous, on an interval that contain the point C. Also, let's assume that both f and g are differentiable on this interval except possibly at C, if both f and g converge to 0 as x converges to C. In the case of continuous functions, means that both f and g equal 0 at C. And the next requirement is extremely important, is that the g prime of x is never 0 on this interval. Then the limit as x converges to C of f prime of x over g prime of x, if that's equal to L, it will imply that the limit of f of x over g of x exists and equals L. This theorem does not imply that if the limit of f of x over g of x, if the second limit exists, that the first limit would exist. It's quite possible for the first limit of the derivative not existing while the limit of the ratio of the original functions exists and is quite finite. Another consideration is that when the limit of f prime over g prime is yet another 0 over 0 case, when that happens, we will have to apply the L'Hopital's rule one more time, and maybe one more time, maybe one more time, to get the result. There are examples when the L'Hopital's rule ends up in an infinite cycle of the applications, when the application may loop to the previous case or may just never end. It doesn't mean that the L'Hopital's rule doesn't work. It means just in that particular case the application of the L'Hopital's rule does not resolve the limit. So in short, what I'm trying to say, if the original limit of the ratio of f and g converges to something like 0 over 0 form, then you can use the L'Hopital's rule, and in the case when this limit exists, then that would imply that the original limit exists as well. Alright, let's go ahead and prove it. By the generalized mean value theorem, we can write that f of x over g of x, which is equal to f of x minus f of c over g of x minus g of c. I'll give you a second to think about why this is true. Yes, it's true because f of c and g of c are both 0, so adding f of c or subtracting f of c doesn't change the equation. And the generalized mean value theorem says that there exists a point, let's call this point z, and this would be equal to f prime of z over g prime of z, where z is between x and c. If x converges to c, then z has to converge to c. Then f prime over z over g prime over z converges to L, and f of x over g of x converges to L as well. This finishes the proof, but I want to stop and reflect a little bit on why the implication is only one way, because it seems like the equality is in both ways. But here's the caveat. When z converges to c, it wouldn't mean that x converges to c. When x converges to c, since z is stuck in between them, then z has to converge to c as well. So we have to investigate the original fraction right here. When x converges to c, z can behave quite wildly, and the existence of the limit of f of x over g of x means that there is a sequence of z values that make the ratio of the derivative converge to the same limit as f of x over g of x. But this implies that this is only true for a particular sequence of z values. It may mean that for some other sequence of z values, this ratio converges to something else. And that is true because x, driving factor here, we can let x converge to c in any way we want. But we have no way to control z. Z converges to c in a particular way it wants to converge to c, and it makes this ratio of the derivative exactly equal to the ratio of f over g, but it doesn't mean that this ratio has to stay the same for all possible z's, or for all possible z's very close to c. So that's why the implication is only one way. We really need the fact that f prime over g prime converges to L. Then we can make the conclusion that for whatever way z may try to converge to c, we will get this limit always L. If we don't have this fact, we can't make the conclusion that the ratio of f of x over g of x will converge to it as well. And if the ratio of f of x over g of x converges to a nice limit, this does not mean that f prime over g prime will converge to the same limit, because the convergence to L will only be observed for the particular z values that are assigned to x's. Anyway, we have another part of this theorem to prove, and before we do that, we need to define what it means for the function to converge to infinity. Let g be a function and c be a limit point of a. We say that the limit of g of x as x converges to c equals infinity if for any capital M larger than 0, there exists delta greater than 0, which means the range of values very close to C, so that when x is closer to C than delta, this implies that g of x is larger than m, which means that if you get very, very close to C, your g of x will be very, very large. So we can make it to be always larger than 1,000,000 or 1,000,000,000, etc. It's just we have to find a small enough interval around C to do it. Notice that I wrote infinity, but I didn't specify positive infinity, but the definition clearly says that we're going to positive infinity. Similarly, we can define the negative infinite limits. It's just m is going to be less than 0, and g of x will be less than m. Given this definition, we can write the second case of the L'Hopital's rule. Suppose f and g are differentiable functions. On some interval a to b, and g prime of x is not 0 for all x in a to b. Since in the case of such infinite limits, most of the time we're going for one-sided limits. Here we're not talking about the interior point C, we're actually going to let x converge to a, and you can see how you can alter the definition of this theorem to also cover the case when x converges to b. So if the limit as x converges to a of g of x equals infinity or minus infinity, then the limit as x converges to a of f prime of x over g prime of x equals L implies that the limit as x goes to a of f of x over g of x also is L. Again, the same talking points apply here. It's just the second limit does not imply the existence of the first. It's only the first. The existence of the first implies the existence of the second. Proof is quite interesting. There is no theorem that will make the proof very short and efficient. We really have to go with epsilons and deltas here. So suppose we have a positive epsilon. Since the limit of the derivative exists, there is a delta so that the difference between the ratio of the derivatives and L is less than epsilon for all x in the interval from a to a plus delta 1. Denote a plus delta 1 as t for any x in this interval from a to t. The generalized mean value theorem applies. Since the derivative is very close to epsilon, we can say that the ratio of the derivative is less than L plus epsilon or greater than L minus epsilon. So this is going to be less than S plus epsilon and greater than L minus epsilon. Now the task is to get rid of the g of t on the bottom and f of t on the top. So the first step is multiply by g of x minus g of t divided by g of x. The only problem that can arise is when this ratio is negative. But since g of x goes to positive infinity, we can clearly see that we can select an interval around a so that g of x will be larger than g of t for all possible x in that interval. So to make sure that this ratio, this fraction, is positive, we choose delta 2 so that when x is in a to a plus delta 2, g of x minus g of t is greater than 0, or g of x is greater than g of t. Since this could be done for any m, in our definition of function going to positive infinity, this can also be done for g of t. So if we multiply this inequality by this, we get L minus epsilon times 1 minus g of t over g of x should be less than f of x minus f of t divided by g of x. It will be less than L plus epsilon multiplied by 1 minus g of t over g of x. The reason why I rewrote this ratio of g of x minus g of t over g of x as this is to emphasize the fact that g of x converges to infinity, and as x converges to point A, this fraction can be made smaller than any epsilon. And here it's the same deal. Now we have to get rid of f of t, but we can do it by simply splitting the fraction and adding this to both sides. Simplifying this inequality will mean the following for the ratio of f of x and g of x. It will be less or equal than L plus epsilon plus, we have a minus sign here, so it's going to be L plus epsilon with a minus sign times g of t plus f of t over g of x, and greater than L minus epsilon plus minus g of t multiplied by L minus epsilon plus f of t, all divided by g of x. Since g of x converges to infinity, we can make sure that these two big fractions are less than epsilon in absolute value. So I can choose delta 3 so that g of x is larger than this numerator divided by epsilon, and g of x is larger than minus L plus epsilon g of t plus f of t divided by epsilon. Set delta to be the minimum of delta 1, delta 2, and delta 3. Then for any x in the interval from a to a plus delta, we have that L minus epsilon. So if the fraction is less than epsilon in absolute value, that is definitely going to be subtracting no more than epsilon from the left hand side. And at the same time, if the fraction on the right is less than epsilon in absolute value, then it's adding no more than epsilon. Simplifying, we get that f of x over g of x would be 2 epsilon close to the value L, and since epsilon was arbitrary small number, it means that f of x over g of x in the limit will have to be L. Let's rewrite this as an absolute value expression. Well, that means that f of x over g of x minus L should be less than 2 epsilon for all x belonging to the interval from a to a plus delta. But that's exactly the definition of the limit when a is the limit point of our interval. Therefore, the limit as x converges to a of f of x over g of x is actually L. Again, I'd like to point out that we only use the fact that g of x converges to infinity to show it. So the L'Hopital's rule will work even in the case when only g of x converges to infinity and f of x converges to a finite limit. But in that case, the resulting limit is quite clear, it's going to be 0, and therefore the L'Hopital's rule is not quite necessary. Anyway, I don't think that working on examples of the application of the L'Hopital's rule is quite necessary at this point, because I'm sure you've done it countless times in your calculus classes. The point was just to demonstrate the proof. And if you're curious, I would encourage you to check out the examples where failing to satisfy one of the conditions in the theorem leads to the conclusions where the L'Hopital's rule seems not to work. Alright, as I said, the second part of this lecture is about a function that's nowhere differentiable. So we're going to look at the function h of x, which is absolute value of x for x in the interval -1 to 1. That's a familiar function. It is differentiable, except at 0. So the procedure that we're going to engage in is we're going to periodize the function and make it periodic with a period 2. So actually, we're going to say that our function h of x can be defined as an absolute value of x minus 2m, where x falls into the interval from 2m minus 1 to 2m plus 1. And I deliberately exclude the right endpoint so that I don't create any ambiguity. So if x is 3.5, that means that m would have to be 2, it will fall into the interval from 3 to 5, and then h of x will be computed as an absolute value of x minus 4, which will give me the absolute value of minus 0.5, which is exactly 1.5. Then I'm going to define a collection of functions, x sub n of x, which is going to be 1 over 2 to the power n times h of 2 to the power n times x. 1 over 2 to the power n scales the function down. H of 2 to the power n of x increases the frequency of the function. So the function oscillations are going to be going faster and faster and faster. And I'm going to define a function g of x, which is going to be the sum as n goes from 0 to infinity of h n of x. This is not the first time you see the function defined as a sum. Take, for example, a Taylor series. Taylor series defined as a sum of the polynomial terms. So the big question here is, well, since each h n of x is continuous, will the g of x be continuous as well? Will g of x be differentiable? And that's the question we're going to answer. I'm going to address the continuity of this function in subsequent chapter 6, where I'm going to show that if the convergence of the series is so-called uniform convergence, details will follow, then if every term of the series is continuous, the resulting function defined as a series will be continuous as well. So let's take it for granted that g of x is a continuous function. And let's look at a much more interesting question of whether or not this function is going to be differentiable. For that, I would like to switch to Mathematica. So here I have my function, and I define x as x minus x rounded to the nearest multiple of 2, which is basically the same thing. So here's the result of this function. We could also experiment with the x modulo 2, but it wouldn't make the definition of this function any simpler. You're more than welcome to try it yourself if you want to. So h x sub n is defined as 1 over 2n, then absolute value of x multiplied by 2 to the power n plugged into this formula. So let's define this function, and let's plot a few examples of this function. So as you can see, it's just the oscillations are increasing in frequency and the function is being scaled down. So the first function goes from 0 to 1, second function goes from 0 to 1/2, then 0 to 1/4, etc., etc. The oscillations become more and more frequent, yet the amplitude of those oscillations goes down. So now let's look at the summation of these functions together. What I'm plotting is one function that results in a summation and the previous one. So here it's a summation of the first two terms with the first term plotted in the background. Here's a summation of the three terms with the previous term in the background, etc., etc., etc. You can see how this function gradually is being constructed. And you can see that there are problems with differentiability now at the point 1/2 and 1.5. Now there's a problem with differentiability at the point 1/4. Not yet the problem with being differentiable at 1/2, but now there are problems with differentiability at 3/4, 1, 5/4, and 7/4. And then at the next iteration, we now have the problem with differentiability at 1/2 that's being preserved at the next iterations. So we can see that the function starts to have problems with differentiability at points like 1/2, 1 over 2 to the power n, or any multiple of 1 over 2 to the power n. We can't really quite see the difference between the functions for summation of first 8, 9, or 10 terms, but the differences here is just not quite visible. It's tiny, but if I zoom in, you will see what's going on. But practically what happens, this function is a fractal, and if I zoom in, I will see this kind of a construction somewhere happening around here, etc., etc., etc. So now the difficult part here is to show that this function is actually not differentiable. We assume the function is continuous, so let's concentrate on this function being non-differentiable. Before we prove it, I want to show, just so that you're sure that the function is well defined, is that this sum actually converges for all x. We can show that g of x is defined as an absolutely convergent sum. The absolute value of the sum is smaller than the sum of absolute values. The original function h was having values from 0 to 1, so h is always less than 1. But hn is defined as 1 over 2n times the value of h, which is no more than 1. But the sum of the terms 1 over 2 to the n is actually no more than 2. So this series is absolutely convergent, therefore it is convergent, and therefore for every x, g is well defined. Now take the continuity of this function for granted. The big question is it differentiable? So at first I want to show that g is not differentiable at 0. Take x to be 1 over 2 to the power m. Then g of x to the power m minus g of 0, which is always going to be 0, divided by x to the power m minus 0, is going to be equal to the sum of 1 over 2 to the power n, as n goes from 0 to infinity, h of 2 to the power n divided by 2 to the power m minus 0 over 1 over 2 to the power m. So it can be written as a sum, as n goes from 0 to infinity, of 2 to the power m over 2 to the power n times h evaluated at 2 to the power n over 2 to the power m. We know the h rises just like x for every point that's less than 1. We can see it in the original graph of h. That's what's going on. And 2 to the power n over 2 to the power m is going to be less than 1 for every n less or equal than m. For every n that's larger than m, we have 2 to the power n over 2 to the power m is a multiple of 2. As 2 to the power 2 times k, where k is some integer. Yes, I know that it's going to be a power of 2, but that's not important. What is important here is that it's going to be an even point, and at each even point, at each even integer, h is exactly 0. So it turns out that the sum is going to be finite. So as we add from 0 to m, we have 2 to the power m over 2 to the power n times the value of h, which is exactly the same as x for all x less than 1. So it's just going to be h evaluated at this point is going to be 2 to the power n over 2 to the power m plus the sum as n goes from m plus 1 to infinity of zeros, because the values of h at these points are 0. So it's going to be adding 1s counting from 0 to m, so it's exactly m plus 1. Therefore, the limit as x goes to 0 of g of x minus g of 0 over x minus 0 doesn't exist. It's not finite. You may say, well, what if it's infinite? It's not, because if we let x to be negative 1 over 2 to the power m, we'll get the result that the derivative is negative m minus 1. So the derivative will go to negative infinity from the other side. We can see it from the graph that here the derivative will probably go to negative infinity. The function is going to be quite symmetric, and so we'll have quite a lot of cusps at these corner points. So I'm going to quickly write it this way. I'm not going to bore you with details, but you can show that the point 1 is also going to be a cusp. Also, g prime 1/2 doesn't exist. Very similarly, we can show that g prime at the points k over 2 to the power m doesn't exist. So this shows that the derivative of the function g doesn't exist at the points of this form, which we call dyadic points, which are just points that can be written as a summation of 1/2 and quarters, etc. So it's just a summation of terms 1/2 to the power m to some power. So you might assume that, well, we only have the derivative failing to exist at this point. But here's the surprising part. Let x not be dyadic, which means that for any m we can find k so that x is going to be less than k plus 1 over 2 to the power m and greater than k over 2 to the power m. So x is always in between two neighboring dyadic points. And with the increase of m, these points will get closer and closer and closer to x. Dyadic points are dense, just like rationals. In any open interval, you can find some kind of a dyadic point there. So we can create two sequences. X sub m being k sub m over 2 to the power m, where k sub m is chosen so that it's less than x, and y sub m being k sub m plus 1 over 2 to the power m, where again k sub m is chosen so that km plus 1 over 2 to the power m is actually greater than x. Both sequences will converge to x. And so now the question is, what is the limit of g of y sub m minus g of x sub m divided by y sub m minus x sub m? If the derivative of g is a continuous function, or if g is differentiable, then I could use the mean value theorem. But the problem is that we already proven that g is not a differentiable function. However, we can try to assume that g is differentiable at the point x. Then the limit above has to converge to the derivative. However, as m goes to infinity, we can show that the limit of this quotient doesn't exist, therefore showing that the derivative at the point x may not exist as well. So I know I didn't provide many details, and I only proved that the function g is not differentiable at 0, and I can kind of assume that it can be done also for every integer, for every dyadic point, and then from every dyadic point you can extrapolate this onto any non-dyadic points, so all other x values. But this is interesting to see that we have a function that is continuous at every point, yet its derivative doesn't exist at all the points where g is continuous. At first it might seem like a pointless exercise, since in real life we rarely deal with functions like that. But for us as mathematicians, it is important to go to such extreme and explore the boundaries and the limits of our definitions and to know exactly what they mean. And that is the importance of this function. In the real life, there are no applications of this function, other than we can see that certain things can fail and we can kind of understand why they fail. And that's the importance of this, is that we know the limits of our math and therefore we can apply it correctly. Anyway, this finishes up our chapter 5, and we're moving into the concluding sections of the book, which are going to talk about the series and sequences of functions, and then we're going to talk about the integrals.